try to, because tomorrow in the last session, I shall try to give the answers to all the pending questions. There may be some pending questions from today's session as well. So in the last session, there were two successive sessions, 1 hour sessions. So we discussed basics of electromagnetic, polarization as founded in electromagnetic theory. And then we discussed polarization through transmission and Malus law. Then we talked about polarization by reflection, Brewster's law, and then refraction, Arago's approach. Then we talked about double refraction, and in the context of double refraction, we talked about ordinary and extraordinary rays, and then how double refraction can be achieved with the use of special kinds of crystal, calcite crystals, and out of calcite you can make a Nicol prism. And then after that we talked about wavefront propagation in birefringent crystals and positive and negative crystals. And then we talked about Huygens' wavefront approach in a uniaxial birefringent material. And there were 3 cases. One of the cases will be important for us today. So I'll just briefly go back to this case. Case number 2. We shall have a good deal to talk about this case. The optic axis is parallel to the refracting edge, but on the plane of incidence. So this case number 2, this is something that we shall talk about today. So today, I think we can follow yesterday's practice. We can have a 50-minute session, and after that we can have a 10-minute break. The 50-minute session will last from 3 p.m. to 3:50 p.m. I think that will be all right. I think Professor Rajendra can please confirm. May please confirm. Hello? You are able to hear? Yes.
Yeah,
yes.
we can hear you.
Yes. So I said that we can have a 50-minute session like yesterday, and then a 10-minute break, and then resume.
Sure.
Yeah. So like yesterday, and at the end of the session, we can try to answer some of the questions, both the sessions.
Sure.
Okay. So today we shall talk about certain, today we shall also continue our discussion, the mathematical and technical discussion on polarization, without reference to quantum computation or quantum information. But tomorrow we shall touch a good deal about this, quantum information. So here, today we shall talk about the superposition of 2 orthogonal waves. So here we have got 2 electric field vectors. They are oscillating. One is oscillating along the x direction. So it's got the unit vector x cap. And the other is oscillating along the y direction. So the 2 electric field vectors are oscillating and they are mutually perpendicular, but they are part of a wave, but these 2 waves are propagating in the z direction. So this is the way the diagrammatic representation shall be of this situation. So here you have the x component, the ex field, and here you have the y component, the ey field, and the z-axis. The propagation is along the z-axis, and the z-axis is pointing towards the observer. So we are the observers. So the wave is propagating towards us, and the wave is happening due to the oscillations of 2 mutually perpendicular vector fields, one along the x direction, namely Ex, and the other along the y direction, namely Ey. And so now we shall have to look at their superposition states. So here vector E, the superposition vector of these 2, superposed vector of these 2 states will be Ex plus Ey. Every term in this equation is a vector term. So let us look at the scalar power component of this thing. So Ex will be E naught x. This is a constant amplitude, and this is the phase part cos kz minus omega t, and Ey will be E naught y cos kz minus omega t plus epsilon. So epsilon is the phase difference between the 2 waves, right? So now we shall have to, when we add these things up, we shall, I mean, these things we shall now on adding what they will be. So let's see. We use basic trigonometric identities over here. Cosine A plus B will be equal to cosine A plus cosine A into cosine B minus sine A into sine B, where A stands for Az minus omega t and B stands for epsilon. So this is the y equation, right? So we take E naught y to one side, and then cos kz minus omega t plus epsilon is written out like this: cos A cos B minus sine A sine B. And cos kz minus omega t we already know is equal to Ex by E naught x. So this first term, cos kz minus omega t, is written like this. And what about, I mean, the sine kz minus omega t? This thing we shall write in terms of the cosine. So it will be sine of an angle is equal to, I mean, sine squared of an angle is equal to 1 minus the cosine squared of that angle. So that identity we have used here. And then we substituted for the cosine by E for cosine by Ex by E naught x. So that is how we have got this thing. And this equation now, we shall, these expressions, we shall now substitute in this equation. So cos kz minus omega t will be substituted by this, and sine kz minus omega t will be substituted by this. And once substituted, this is what we get. Ex by E naught x is the cosine function, and square root of 1 minus this will be the sine function. After that, we shall have to work a little around things a little around algebraically. So we take the cosine epsilon part to one side, and after that we square the whole equation. So it will be Ey by E naught y minus Ex by E naught x into cos epsilon whole squared, and the right hand side on squaring will give this. Okay. After, and then once we have this thing, we expand it, this part, Ey by E naught y whole squared, Ex by E naught x whole squared. I mean, this is just A minus B whole squared. That is what we have on the left hand side. And on the right hand side, we have got sine squared epsilon minus Ex by E naught x whole squared, sine squared epsilon. Okay. And then once we have this thing, this sine squared epsilon stays on this side. Minus Ex by E naught x whole squared sine squared epsilon will be taken to the left hand side, and this cos squared epsilon, this minus will become plus on the left hand side. So cos squared epsilon plus sine squared epsilon, the two will add up to 1, and these two terms will give this Ex by E naught x whole squared. Then you have Ey by E naught y whole squared minus 2 Ex by E naught x, Ey by E naught y cos epsilon is equal to sine squared epsilon. So that is the superposition state. So the wave is coming, so a superposed wave is coming towards us. We are the observers. One oscillation is happening along the x-axis, another oscillation is happening along the y-axis, and the two waves are not in phase. There's a phase angle difference of epsilon between the two. So what will be the outcome of that is this expression. Now what we shall do is to put in special values of epsilon and see what the resultant oscillatory state or the superposed state will be like. So the simple first case that we shall take up in this equation, we shall put epsilon is equal to 2m pi, where m is an integer, positive integer, even multiple of pi, 0, 1, 2, etc. It will go. And so m into 2 pi, or effectively it is m into 360 degrees. So basically, it will just be the same thing. There will be actually no phase difference. Effectively, this is what it means. So when you have epsilon is equal to 2m pi and m is in an integer 0, 1, 2, etc. So effectively, it will become even multiple of pi. So in that case, we will have sine of epsilon will go to 0 and cos of epsilon will go to 1. Okay, so once we have this thing, so then we can put this here in this equation. So cos of epsilon will become 1, sine epsilon will be 0. So this will just be a perfect square on the left-hand side. Taking the two, all the terms together, it will be this, ex by e naught x minus ey by e naught y whole squared is equal to 0. And then ey will therefore be equal to e naught y by e naught x into ex. Now, e naught y and e naught x are constant quantities, so constant amplitudes of the two components. So basically, if you have to plot this function on the plane, so it will be like this. So this is the superposed wave front. I mean, the wave that is coming towards us. It is oscillating. It will go to its maximum here, and then it will come down to its minimum here. And this oscillation, so Ex is oscillating along the x direction, Ey is oscillating along the y direction, and their superposed state is oscillating along this inclined axis, making an angle of tan inverse E naught y by E naught x with respect to the x-axis, the horizontal axis. And so effectively, there is no phase difference for this thing. Now, let us look at case 2. This will be an odd multiple of pi. So 2m plus 1 into pi, right? So that will be effectively like a multiple, some m into 180 degrees. So sine of epsilon will be equal to 0 in this formula. Sine of epsilon will be 0. Cosine of epsilon will be equal to minus 1. So there we have this thing. So once we have this, then in this equation, this is what we have. Right hand side will vanish. This minus 1 and this minus 2 will together will become plus 2. And so this will be once more a perfect square. Ex by e naught x plus ey by e naught y whole squared is equal to 0. Therefore, ey will be equal to e naught y by e naught x into ex. So if I were to plot this, basically this is a phase difference of 180 degrees. So completely opposite to the previous case. So here the oscillatory state, because now once again, just let us try to understand. Ex, the oscillation is happening along the x direction. Ey, the oscillation is happening along the y direction. But their superposition state will oscillate in the second and the fourth quadrant. So this is the tip of the wave vector. So this inclined line is actually a plane, but we are not able to see the plane because we are looking down the z-axis. So the plane looked edge on is looking like a line. But this is actually a plane that is progressing towards us, and this on this plane the electric wave vector is oscillating as it is progressing, approaching us. Similarly here, except that in this case the electric field vector is oscillating along in the first and the third quadrants. Okay, so these two cases were linear superposition states. Now we shall look at uh, some different, something much more different than this. What if the phase angle difference is plus minus 90 degrees or plus minus pi by 2? So, and of course, there could also be 2m pi. So, effectively, an integral multiple of 360 degrees. That's not really a phase difference. So, here you have got plus minus pi by 2. In that case, sine squared epsilon will be equal to 1 and cos epsilon will be equal to 0. And our equation then will be reduced to, so both the phase angle terms will go away. So we'll just be left with Ex by E naught x whole squared plus Ey by E naught y whole squared is equal to 1. Is the screen not visible? Professor Rajendra, please confirm. Hello? Is there some issue with this viewing the screen? Hello?
Yes,
Screen is visible, right?
screen is visible.
Okay, okay. Because someone just posted a comment, I thought I'd just confirm.
No,
Visible.
no,
Okay.
screen is visible.
Thank you very much. Okay. So what we have here is this. So here. So this is now a case of elliptical polarization. The wave vector, the superposed wave vector, will have a tip that will be sweeping out, that will sweep out an elliptical orbit, right? And when both the vectors have the same amplitude, E naught x and E naught y are the same, then this ellipse will become a circle, I mean, a circular profile. So uh, this is what we have. Okay. Now, it's one thing to say they are elliptical or they are circular, that is all right, but what is the direction in which the ellipse or the circle is being traced out? Is it clockwise or is it anti-clockwise? So when epsilon is equal to plus pi by 2, then it is anti-clockwise. So remember, in the convention of angles, anti-clockwise is positive angle. So here plus pi by 2. And so that anti-clockwise motion is left circularly polarized light. So anti-clockwise superposition will give us left circularly polarized light. And when the phase angle difference has got a negative sign, negative angle means it is going in the clockwise direction. In that case, you will have right circularly polarized light. The convention is that it is progressing towards the observer. Right circularly polarized light will have this minus pi by 2. So left and right is to be defined from the point of view of the observer. The wave is progressing towards the observer, and there and along the track, left and right, or clockwise and anti-clockwise motion is being executed in the superposed state. So we shall look at this thing in a little more detail, I mean more formally. So here is a situation. Let's just take circular polarization because we are now interested only in the direction of the angle, not the amplitude. So E naught is a common amplitude for both the X state of oscillation and the Y state of oscillation. And the phase angle difference between the two is epsilon. And we are just looking at a wave that is frozen on the XY plane. So basically, it is Z equal to 0. Later, we will release Z to have different values. So on Z equal to 0, Ex will be equal to E naught cos minus omega t, and that will be equal to E naught cos omega t. Ey will be equal to 0 t, of course, will be E naught cos minus omega t plus epsilon. So it will be cos of minus omega t whole minus epsilon. But cosine function is an even function, so negative signs will not matter. So this both of them, cos of minus omega t and cos of minus omega t minus epsilon will just become cos omega t and cos omega t minus epsilon. And once we have that, then we can test with the values of epsilon and t. Sorry. So Ey will be equal to E naught cos omega t plus pi by 2 uh, because there's minus epsilon over here. So when I put minus pi by 2, this thing will become plus pi by 2. And cos omega t plus pi by 2, this is the little algebra trigonometry that we have worked on here. It will be cos pi by 2 plus omega t. So cos pi by 2 minus of minus omega t. And so cos of 90-degree minus an angle will be sine of that angle. So sine of minus omega t, which is minus sine omega t. So this is what we have when E for Ey for a phase angle difference of minus pi by 2. Okay, so we have these two states frozen on the z plane, I mean xy plane, z equal to 0. Ex is equal to E naught cos omega t, and Ey will be equal to E naught cos omega t minus epsilon, which is equal to minus E naught sine omega t. So at t equal to 0, Ex will be equal to E naught cos omega into 0. Cos of 0 will be 1, so Ex will be equal to E naught. And Ey will be equal to minus E naught sine omega into 0 will be 0. So if I want to represent that thing graphically, this is what we shall get. At t equal to 0, E naught, I'm sorry, Ey is 0, meaning it's at the center, at the origin. Whereas Ex is equal to E naught, it is over here. Now what we do is that we make time progress. So after the elapse of a time of pi by 2 omega, time is positive. So in that case, once that has happened, this is what will result. E will be equal to, Ex will be equal to E naught cos omega t. T is equal to 2 pi by omega. 2 pi by omega, omega and omega will cancel. And so when you write omega t is equal to pi by 2, and t is therefore will be equal to 2 pi by 2 omega, this is what you will get. Ex will be equal to E naught into cos 90 degree. That will be 0. And Ey will be equal to minus E naught sine 90 degree, or pi by 2. That will be minus E naught. And so at t equal to 0, Ex was aligned along the horizontal axis and Ey was 0. After some time, at t equal to pi by 2 omega, E naught has become 0. Ex has become 0. I'm sorry. Ex has become 0, whereas Ey has become minus E naught. So this line swung down, or this arrow has swung down to this arrow. Now, this is a clockwise rotation, right? Circular polarization, clockwise rotation, and it corresponds to this negative angle of minus pi by 2. We shall put a positive angle now and just test for ourselves. Epsilon will be equal to plus pi by 2. So we put the positive angle value also. So in the second case, Ex is equal to E naught cos omega t, Ey is equal to E naught cos omega t minus epsilon, and epsilon is equal to pi by 2. Therefore, Ey will be equal to E naught cos omega t minus pi by 2, and that will be, this will be cos of pi by 2 minus omega t, because the minus sign will be killed. And so Ey will be equal to E naught cos 90 degree minus omega t, that will be sine omega t. And so here this will be E naught sine omega t, and Ex will be E naught cos omega t. So at t equal to 0, let us now see. At t equal to 0, Ex will be equal to E naught and Ey will be equal to 0. But when omega t will be equal to plus pi by 2, or pi by 2, so this thing will swing in this direction. We can check for ourselves. Ex will become 0, whereas Ey will become plus E naught. So from here, the arrow that was lying flat on the ground will pick up and it will become vertical here, this way, at on the xy plane, which has the coordinate value z equal to 0. Okay, so once we have this, then we can see that it is moving in the left direction or anti-clockwise direction. So that is anti-clockwise rotation. Now we have done this thing for the plane z equal to 0. This could happen on any other plane when z is some other value, z is equal to z naught, where the value of z naught is not equal to 0, so away from the xy plane. And so there also you can write this thing instead of z, you'll just write z naught. And so this is how it will be. So basically this will be, earlier when z was equal to 0, our reference axis was x. That was the first axis, and the second reference axis was y. When I put z equal to z naught, the two reference axes will be rotated by an angle kz naught. That is all there will be. Otherwise, all other arguments will hold regarding the clockwise and anti-clockwise rotation here. So that so we just now have to remember one thing: plus angle phase difference means anti-clockwise rotation, and minus angle phase difference will be clockwise rotation. Okay. So with all of these ideas now, we can discuss ways and means of changing polarization states. Okay, now so far we have found ways to achieve polarization, reflection, refraction, double refraction, transmission, all sorts of things. What we shall do now is to look at the way a polarized light will change its polarization state to something like linear polarization or elliptical polarization or circular polarization. So in order to do that, we shall have to refer to what we discussed earlier. I shall get back to that point. So the device by which the polarization state of a certain polarized light can be changed is known as a retarder. So these are devices to change the polarization of an incident wave, usually made of calcite, which is a birefringent material. Okay. And so the way to do this thing is to make the normal incidence with optic axis parallel to the refracting edge. So the incident light will fall normally on the retarder material, and the retarder material will be arranged in such a manner that the optic axis will be parallel to the refracting edge. That shall take us to what we discussed at the end of the last session yesterday. Uh, so I'll just get back to that. Today, even at the start, I pointed it out to you. This is the case that we have. This is the refracting edge, and this is also the optic axis. So this corresponds to optic axis parallel to the refracting edge. So here, optic axis is parallel to the refracting edge, but on the plane of incidence, on the plane of this paper, and that is the case that shall be useful for us in designing a retarder plate. This is the graph that we have. The uh, extraordinary ray is progressing faster than the ordinary ray. Once again, I shall remind you that ordinary rays progress with a spherical front, whereas extraordinary rays progress with an elliptical front. So, because extraordinary rays are the outcome of anisotropicity in the crystal, so in different directions, light will travel with different speeds. As a result, the wavefront will become an elliptical wavefront. So here we have this. Let's see. Uh, here. So normal incidence with optic axis parallel to the refracting edge. The plate or the retarder, it has a thickness of D, and optical path. In geometrical optics, optical path is defined as the path traveled by light, the geometric path traveled by light multiplied by the refractive index of the medium in which light has traveled that path. So there are now two refractive indices. The ordinary ray has a refractive index of NO, and the extraordinary ray has the refractive index of NE. And so the optical path traveled by the ordinary ray will be NO into D, and the extraordinary ray will be NE into D. And the optical path difference will therefore be D times NE minus NO. We have just taken the absolute value because, so that will be the this path difference, optical path difference. We have taken the absolute value because we don't know whether NE will be greater than or less than NO or not. So that's the reason why, because this number always has to be positive. So even if the whatever is the argument over here is not positive, even so, we will just take the positive absolute value. So here is a schematic representation of what happens in the case of a retarder plate. So here is a calcite material, it's birefringent, doubly refracting, and outside is air. So light has fallen on this edge. Now, this light contains two states of polarization. One is due to in-plane oscillations as drawn by this wave and on the page, on the plane of the paper. and the other is off the plane oscillations represented by these heavy black dots. They come out and then they go in. Okay, so once it has entered the calcite material, the crystal material, immediately the ordinary and the extraordinary rays will be separated from each other, and the extraordinary rays will travel faster in an elliptical with an elliptical wavefront, whereas the ordinary rays will travel with a spherical wavefront. We are looking at this picture side on. As a result, the ordinary rays have been drawn with a wavefront that is looking circular. The orange track here, this orange track is a two-dimensional collapse on this plane of a three-dimensional spherical wavefront. And here, the green track or the green curve is the wavefront of the E rays, or rather the projection, three-dimensional projection of the three-dimensional wavefront on the plane of the paper. Okay, and the thickness of the retarder plate is D. Let us now analyze it. Well, looked close, this is what it will be like. This is to the left of this vertical line, the light that has arrived contains both in-plane oscillations and off-the-plane oscillations. To the right, only the in-plane oscillations are progressing. That is the passage of the extraordinary rays. Whereas for ordinary rays, uh, the same light will then enter the calcite material with a spherical wavefront, but with only the off the plane oscillations, these black dots. So that is how extraordinary rays behave. And the velocity of the light in the two cases, for the cases of the two wavefronts, will be VE. So velocity is the speed of light in vacuum. Velocity of light in a medium is the speed of light in vacuum divided by the refractive index of that medium. So VE is equal to C by NE, and VO is equal to C by NO. Okay, so in the former case, or the first case, you have optical path equal to NE into D, and in the second case, it is NO into D. And the optical path difference we have already seen for ourselves. Okay, so now we shall have to work on this thing a little. So we know that phase difference will be equal to, phase difference by 2 pi is path difference by the wavelength. So that is the unitary balance that we maintain. Phase difference by 2 pi is equal to path difference by the wavelength. So path difference is this lambda. K is equal to 2 pi by the wavelength, where this wavelength is a special kind of a wavelength, lambda O cut, as in 0, right? So that's the vacuum wavelength. So the left-hand side, this equation should be read as delta phi by 2 pi, that is phase difference by 2 pi, is equal to capital lambda, which is the path difference, divided by lambda as in the vacuum wavelength in vacuum. Okay, so delta phi will be equal to 2 pi by lambda into the path difference is d into Ne minus No, as has been written a little more clearly in this small panel here. Okay, so when you talk about a full wave plate, let us now see this formula. D will be equal to delta phi into the vacuum wavelength divided by 2 pi into divided by Ne minus No. I'm taking the absolute value. So we shall now look at different cases. So delta phi is equal to 2 pi, which is an even multiple of pi. So what we will have over here is so 2 pi by the wavelength into the path difference is equal to 2 pi. So there will be a cancellation, and the path difference will simply be the wavelength in vacuum divided by the refractive index difference. So there is no phase shift in this case, because having a phase angle difference of integral multiples of 360 degree and positive integral multiples, well, there's also 0. So when you even multiples of pi, or integral multiples of 2 pi, that is, then there is no phase shift. And in that case, the necessary retarder plate thickness is given by this formula, wavelength divided by the difference of the two refractive indices. What if the phase angle difference was pi, instead of in the previous case, in the retarder plate, we introduced a phase angle difference of 2 pi, so we get a full wave plate. The condition, this is the phase angle difference, delta phi is equal to 2 pi, and so it's an even multiple of pi. So now what we shall do is half wave plate, we shall put an odd multiple of pi. So delta phi is equal to 2 pi. So in this formula, 2 pi by the wavelength is equal to d into the difference of the two refractive indices is equal to pi, which is 180 degrees. And so d will be equal to this whole thing, lambda naught by 2. And so that is the phase difference that we shall end up getting. Okay, so this is the phase difference that we have. Okay, so now, so what is the outcome? In the previous example, when there was a phase difference of integral multiple of 2 pi, there was no phase shift for this for this case. But now, what we shall see is that if you have an oscillation of the first polarized light in the first quadrant, then the half wave plate will cause it to rotate. Uh, Someone is asking a question. Mr. Manoj Kumar ji is asked a question. Yes, there's a book. You can look up Eugene Heck's book. All these things are given very clearly. There's also a very handy and simple book with numerous problems written by two Indian authors, Brijlal and Subramanian. But at the end of the class, I'll mention. You can put this question. So, I mean, books on optics contain all these things. In Eugene Hecht, these things, the ones that I'm showing, are from Hecht's book. It's a very good book, really, in that sense. But you can also look Brijlal and Subramanian for simple problems to work on. For concept building, that's also a good book. Okay, so so this here, a plane polarized is in the first quadrant. If you make it undergo a phase change of pi, it'll go into the third quadrant. As in this diagram, we have already discussed that. We have talked about the polarization state shifting. Let me just go back to that point once again. You introduce phase angle difference of, sorry, here, pi. 2m pi is effectively the same angle, I mean, same phase, but phase angle difference of pi. What will happen is that from the first quadrant, it will go to the third, first quadrant, it will go to the second quadrant. I think I don't know, I mean, I think I may have just mistakenly mentioned going from the first to the third. Is going from the first to the second. So that is what you have here. That same situation is obtaining here too, that here this is what you have. You shift from the first quadrant to the second quadrant by this angle. The same angle will be the same. So effectively rotate the plane of polarization of linearly polarized light by 2 times theta. So the theta is measured with respect to the vertical axis. Then you have the third case. So we have talked about two cases, uh, full wave plate, meaning that in a full wave, the phase difference will be equal to, for a full wave, the phase corresponds to 2 pi. For a half wave, the phase corresponds to pi. And for a quarter wave, the phase angle corresponds to pi by 2. Okay, so now let us look at the last case, quarter wave plate, when we take it to pi by 2. So here we write delta phi is equal to pi by 2. And after that, you can see that d will be equal to quarter wavelength, wavelength divided by 4. In the previous case, it was wavelength divided by 2, hence half wave. Here in the first case, it was wavelength divided by 1. Of course, there's also the difference of the two refractive indices. That's a non-zero difference, but otherwise lambda by 2 gives the name half wave. Similarly, lambda by 4 gives the name quarter wave. The two pi's will cancel, and this is what we have. So in this case, you will have elliptical polarization. You make plane polarized light fall on a quarter wave plate, the light that will emerge. So basically, diagrammatically, it will be like this, that this is your wave. I mean, this is the retarder plate. This is the first phase, and this is the second phase. In between these two phases, there's calcite material. This is air to the left, and there's air to the right. So polarized light will enter, and if it's a full wave plate, it will not change anything. It will emerge on the other side as it is. If it's a half wave plate, its orientation, plane of polarization will undergo a 2 theta change from the first quadrant to the second quadrant. But if it's a quarter wave plate, then the wave will emerge with an elliptical state of polarization, as we can see from here. So, and of course, if the two amplitudes are equal of each other for the two waves Ex and Ey, the two component waves, then in that case, the polarization will become circular. So elliptical polarization is more general without equality of the amplitudes of the two components, but in the case, but the phase angle difference must be pi by 2. But if you want circular polarization, in addition to pi by 2, you will also require equality of the amplitudes, the wave amplitudes. Okay, and so now we can move on to discussing some cases, the analysis of polarized light. Suppose some polarized light is given, so we do not know what is the state of that polarization. So how will you know what it is? So let us look at those possible cases of polarization. There are 5 cases. One is plane polarized light, which means that the oscillation is confined to oscillation of the polarized superposition state is confined to a plane. The second case is elliptical polarization. Elliptical polarization means that the tip of the wave vector, as it is progressing towards the observer, is tracing out an ellipse as it is moving forward. So, from the point of view, actually, it will not be tracing out an ellipse if you look at it side on. It will be tracing out something like a helix. Well, that will be more true for the case of a circularly polarized light. A circularly polarized light is, I mean, the light is like a train coming towards the observer, and the tip of the polarized light vector is tracing out a circle looked at viewed head on. But if you look at it side on, then the tip of the polarized vector in 3 space is will trace out a helical path. Similarly, for elliptical polarized light, except that the radius of that helix will keep changing. Once it will go to a maximum, and then again corresponding to the major axis of the ellipse, and then to a minimum corresponding to the minor axis of the ellipse. Then there's partially polarized light, meaning that there could be one polarized light mixed with some unpolarized light, and then the whole thing could be randomly polarized or completely unpolarized. So we shall look at these 5 cases and try to see how they could be distinguished from one another. In order to do so, we shall use Malus law, where intensity of a polarized state depends. So polarized light is made to fall on a polarizing material, which we actually called analyzer, because this whole topic is an analysis of polarized light. So in polarized light is made to fall on an analyzer, and then the analyzer is rotated. And so the light that emerges out of the analyzer will be proportional to the intensity of the light that emerges will be proportional to the square of the cosine of the angle between the plane of polarization and uh, the alignment of the analyzer, I mean the crystal planes. So let's now see. So that is what we have done. Let's look at plane polarized light first. So here we have plane polarized light. Its orientation state is like this: x-axis horizontal, I mean for reference frame, x and y, and the light is just oscillating in the first quadrant, well actually first to the third quadrant. So that's the plane polarized state. Now you make this thing pass through an analyzer, a crystal, what will happen? Simple polarizer, I mean, an analyzer is actually a polarizer. So when the angle between the polarization orientation and the crystal planes will be 90 degrees, then cos squared 90 degree will be 0. So such a state will be in a full cycle, such a state will be achieved twice. So twice the angle between the elliptical plane, I'm sorry, the angle between the linearly polarized light and the crystal lattice planes orientation will be uh, 90 degrees. So on these two occasions, over a full cycle of rotation of the polarizer, zero intensity will be obtained. So that will tell us that it is plane polarized light. Now suppose we have elliptically polarized light. So this will be the rotation of the tip of the electric field vector. So you make the elliptically polarized light pass through a quarter wave plate. So elliptically polarized light already has a phase difference of pi by 2. So once you make that light pass through a quarter wave plate will add another pi by 2 phase difference. So together it will become pi, and immediately it will become linearly polarized. After that, if you make that light pass through a polarizer, it will be just like the previous case, that it will get this in this second polarizer, you will get zero intensity two times in one full rotation of the polarizer. Okay, and if you do not put the quarter wave plate, then for elliptically polarized light, the intensity will vary between a maximum value and the minimum value. When will you get the maximum value? When the crystal lattice plane of the polarizer will align along the major axis of this ellipse, then you will get maximum, because intensity is square of the amplitude. So the maximum amplitude is along the major axis of the ellipse, and the minimum intensity will be along the minor axis of the ellipse. So square of the amplitude of the electric wave will give us the intensity. So without the quarter wave plate, the intensity will vary between a maximum and a minimum value as it is made to pass through the polarizer. Then circularly polarized light, it's again the same thing. It's a special case of the previous discussion, elliptical polarization. You make the circularly polarized light pass through a quarter wave plate. Again, it picks up a pi by 2 phase difference. It already had a pi by 2 phase difference. Together, it will become pi, and so it will become linearly polarized. And when passed through a polarizer, it will show zero intensity twice. And without the quarter wave plate, the intensity will remain constant, because the amplitude is constant everywhere, amplitude of the electric field vector. So whatever be the orientation of the lattice planes of the polarizer, it will not matter. The intensity will remain the same without using the quarter wave plate. Now, the fourth case that we take up is of partially polarized light. It's a mixture of linearly polarized light and unpolarized light. So you put a quarter wave plate, so the linearly polarized light will become elliptically polarized, right? So an unpolarized light is randomly oriented, so that will not make any difference. But since you have converted uh, this linearly polarized light to elliptically polarized light, then when passing through the polarizer, the intensity will vary between a maximum and a minimum value that you have. Okay, so that's the fourth case. And the fifth case is randomly polarized light. All polarization states are there, so it doesn't really matter, regardless of using whether you use a quarter wave plate or not. It will not matter. The polarizer will always show the same intensity, because all states are now there. It's a completely random mixing. So that finishes our discussion on the use of retarder plates. If anyone has a question or anything, we can take up the question, or we can just take a break for 10 minutes, if that is all right. Professor Rajendra, may please confirm.
I mean, we can take the questions when you start the next
Oh,
session,
okay,
probably.
okay, okay, okay. Fine, fine. That is all right. So in 10 minutes, we can meet. It is now 3:50. We shall meet at 4 then, right? Okay.
Yes.
Thank you. Thank you.
So can we start?
Hello,
Yeah,
we can start now, I think.
sure,
So,
sure.
okay.
Can
So, has any question been asked? Could you please just check?
yes, there are few questions.
Okay, perhaps we can take those questions now. You can hear me clearly, I hope.
Yeah, yeah, we can hear you clearly.
Okay, okay.
कोई क्वेश्चन तो मुझे मिला नहीं सब जनरली है
So there is a general question, not so technical. It's related to somebody is asking any book available to understand the mathematics which is being discussed here.
I think I also answered that वो जब वो चल रहा था I saw the question flashing on. So
Uh-huh.
देखिए I mentioned to you the mathematics that I discussed about retarder plates, full wave plate, and all those things, and those superposition of orthogonal waves, all those states, how difference, all of those things, they have been taken from Eugene Heck's book, right? And retarder full plates and all those things, they have been taken from Eugene Heck's book. But if someone, I mean, if it's a question of the mathematical part, there's also another book by two Indian authors, Brijlal and Subramanian. Optics, I think, is the name. Just you can just please check Brijlal, Brijlal. Just if you could type Brijlal and optics, I think you'll get the name of both the names of both the authors, Brijlal and Subramanian. So there, that book has a certain advantage that several problems, numerical problems, have been solved. So that could help in understanding of concept building and understanding the mathematical aspects of this subject. But otherwise, Eugene Heck's book is also very good. I mean, the longer derivations and all these things, they are very good in Eugene Heck's book. And though I've taken from that book only, particularly Heck's book stresses a good deal on the electromagnetic aspects of polarization. Right, Jenkins and White is a classical old optics kind of a book. It's a very good book, no doubt, but Eugene Hex brings in this electromagnetic flavor. So stresses on the electromagnetic flavor much more than Jenkins and White. And for the mathematics part, numericals and everything, detailed and everything, one could look at Brijlal and Subramanian's book. Not that I've prepared the notes from that book, but for working out math problems in polarization or in general optics, that book is okay. So I think we could start after this.
There is one more question. What is the purpose of all these rotation angles of polarizations? So probably, I mean, the thing is, these are the fundamental topics which are being addressed so that if somebody wants to implement qubit and all, then using photonics, then these things becomes very relevant.
Yes, yes. So tomorrow, what will happen is that today in the we are about to begin the fourth class or the fourth session. So in the fourth session, we will complete the basic ideas of polarization, and tomorrow in the fifth session, we shall refer to the quantum computation or quantum communication aspects of polarization. Not that I know much about that, but I can touch on some things about polarization that could be relevant from the point of view of quantum communication. Someone just asked what is the relevance of all these wave plate and all that. So the next few topics that I'm about to begin will show that these things are of great importance in biological kind of problems. We shall soon see. For instance, I mean, for someone who is heavily diabetic, uh, urine contains sugar, and sugar shows optical activity. Just the title. If you can see the slide, can you see the slide right now in
Yes.
front? Yes. So sugar shows optical activity. So the greater the amount of sugar, more will be the optical activity. So you can draw biological inferences also from the phenomenon of polarization. So those are, I mean, polarization is a, I mean, I mean, my purpose in discussing all these things is to show that there's a wide range of application. And tomorrow we will specifically discuss certain aspects of quantum information too. So that is the idea. So perhaps we can start, I think.
There are few more questions. The same question, but in a different word. So, can we go for generation of quantum gates through this polarization concept? So, as we have discussed, these polarization concepts are used to build a qubit using photonics. So, essentially, once you have qubits, you can go on upper levels of designing and design the quantum gate. So, essentially, if I mean, these concepts are being used to implement a qubit. A simple qubit can be implemented using these photonics.
That I do not know. Someone is asking what is quantum medication. Well, I do not know that. But no, but see, polarization, just now we talked about, just in the last session, we talked about superposition, right? Superposition is achieved through the superposition, through two orthogonal states. The superposed state is achieved through the superposition of two orthogonal states. So in quantum mechanics also you have that thing, there's a zero state zero and there's a one state, and then you'll have all these intermediate states which are superpositions of the two basic states. So it's somewhat
Right.
like polarization. And
Yeah,
also
exactly.
let us
Yeah.
not forget something. Polarization is to deal with light, and light is also a quantum particle, photon. Right. So there's a good deal of overlap. I mean, it can't be okay. I do not know, but I saw some university studying on quantum medicine or whatever. But unfortunately, I mean, I don't know much about. I mean, anything about this subject actually. Yeah, I mean, quantum mechanics can have a wide range of applications in so many areas. So I shouldn't be surprised if these things are happening. Anyway, so perhaps we could now get underway with the technical discussion at hand, right?
There is one more question, how
Right.
the polarizer can be used in quantum simulation models. So basically in quantum simulation models, you generally assume that you already have the qubit there. So basically, I mean, you already have qubit and then you try to build the quantum circuits out of it. Here, when we are discussing these topics, we are, I mean, these concepts can be used to build a qubit. Once you have qubit, you can build the simulation model over it. So in quantum simulation models, we don't assume the physics behind how we are going to implement the qubit. So there are multiple ways of implementing qubit. Here we are discussing only the part where qubit can be implemented using photonics. I hope this answers that question.
Okay,
Uh,
so Professor
Now
Rajendra has
we can
answered.
start the session.
Yeah, yeah. So I will just briefly round up what we talked so far today. So we talked about the superposition of two orthogonal waves, one oscillating along the x direction and the other along the y direction. And then due to the phase difference between these two states, we can achieve various states of polarization, plane polarized, light, elliptical, circular polarization. And then we use these properties to study the outcome of retarders. So we talked about full wave retarder plate, half wave retarder plate, quarter wave retarder plate, and how they can bring about various states of polarization, and then how these polarized states could be analyzed. So those were the topics that we completed. Now we shall talk about optical activity. So these were the topics we just completed. We shall now take up the case of optical activity. This is actually a subject of great importance in biology. So, although the basic purpose of this program is to talk about the relevance of polarization in quantum uh, information theory, but we can still broaden the scope of the subject. I mean, polarization is a phenomenon that has been known for the last 200 to 300 years. So there was no quantum mechanics at the in the early stages of polarization. So I think it might be a good idea to appreciate the broadness of this subject. So let us now try to see what it is. Optical activity is the rotation of the E field. Let's try to understand. So plane of vibration of a beam of linearly polarized light undergoes a continuous rotation as it propagates along the optic axis of a quartz plate. So this was how it was seen. Let's just try to understand it with reference to some of our previous diagrams. So here is plane polarized light. It is passing through. So it has got an X component and it has got a Y component and it is traveling along the Z axis. So as it is traveling along the Z axis through an optically active material, what will happen is that this plane of oscillation will continue to rotate as it is traveling forward, right? So if you were to just look at it head on, I'm sorry, you will just see that this plane is rotating. So it could rotate in the left direction, it could rotate in the right direction. But actually, it actually is moving forward also. So it will keep rotating and then and eventually come out of that polarizing material or that optically active material with a new state of polarization. Let us now try to see this plane of vibration. That diagram showed that this is a plane of vibration. Where is the plane? The plane is actually, you're looking at the plane edge on. That's why it is looking like a line. So this is a plane of vibration. And this plane of vibration will rotate continuously in as the light passes through a linearly polarized light passes through an optically active column of material. So plane of vibration of a beam of linearly polarized light undergoes a continuous rotation as it propagates along the optic axis of a quartz plate. In this case, of course, we are talking about quartz plate. Now it can be many various other things also, many other substances. So the rotation can be either right-handed, in which case you call it dextrorotatory, or it can be left-handed, in which it is levorotatory. Dextrorotatory means clockwise rotation. So, and levorotatory means anti-clockwise rotation. So convention is look in the direction of the source. So if you look in the direction of this, the light is coming towards you, you're looking at it. If this arrow, inclined arrow goes down, rotates downwards like this, clockwise, then you have dextrorotatory, right-handed. Dextrorotatory is right-handed rotation. And if it goes up this way, anti-clockwise, then it is levorotatory. So the light is passing through a long column of optically active material. So optical activity is just the phenomenon of rotating the plane of polarization of a linearly polarized light. Uh, just to expand the relevance of this thing in more broadly. So dextro levorotatory behavior in quartz depends on the left-handed and right-handed structure of the quartz material. So in chemistry, these are called enantiomorphs. So quartz can come in a left-handed form and a right-handed form. So if you make light pass through the left-handed form, you'll get one kind of rotation, and the opposite kind of rotation you'll get for the right-handed form, dextro form and the levo form. So enantiomorphs are mirror images of each other. So in chemistry, you have this sort of a thing that the molecular formula may be all right, but the arrangement can make a good deal of difference in the chemical behavior of a certain substance. I mean, the atoms are there, the molecular formula is also the same, but the way you arrange the molecules and the atoms, and in this case, the arrangement is like a mirror image of, one left-handed quartz will be the mirror image of right-handed quartz. Just like if we stand in front of a mirror, if we are right-handed, for instance, I am right-handed, what I will see is that a left-handed image of myself. So like that. Okay. Uh, Now you notice one thing, that molten quartz is not optically active. So the molecular behavior is not important over here. Quartz will continue to remain quartz even in fused molten state. So there it will not show optical activity. Then clearly the optical activity is dependent on the crystal structure of quartz, right? So there you can see the arrangement of molecules and atoms are important over here. And that way you can make a distinction between various cases. So in chemistry, of course, if the molecular formula is the same, then how will you distinguish it? You have to make use of polarization if there are these differences. So optical activity can be seen in liquid and vapors of turpentine. So there you can see something. Whereas quartz will not show optical activity in the liquid phase or molten or fused phase. It will show optical activity only in the crystalline form. It's the other way around for turpentine. In liquid or vapor, fluid phases, it will show optical activity. Okay. What about sugar? I just mentioned to you just a while ago that sugar will show optical activity in a solution. So you mix dissolved sugar in water, the sugar solution that you have will show optical activity. So in all of these cases, the optical activity is a property of the molecular structure, not of the arrangement, because there is no arrangement. In liquid form or gas form, vapor form, there is no arrangement. So the optical activity is the outcome of molecular properties. So you can see that there's so much, I mean, such a vast range of polarizing behavior of various things. Quartz will show it in polarizing behavior in crystal form. These things, sugar and turpentine, they will show it in the fused or the vapor form. So all sorts of things. Then something even stranger for this substance, rubidium tartrate. It will show levorotatory behavior in the crystalline state, but it will show dextrorotatory behavior in the solution state. So, in the solution state, it will go the other way around, but it will not, in the crystalline state, it will not show this behavior. So, I mean, there are so many strange things. So, what we shall do, I mean, I hope I have motivated the phenomenon of optical activity enough. Um, it's a vastly interesting subject. Stereochemistry and all of these things are dependent on that. So, as you can see, it's got implications both in biology and in chemistry also. Like I mentioned to you, sugar solution, then there will be amino acids. They also can show dextrorotatory and lever amino acids. I'm sorry, show levorotatory behavior, not dextrorotatory behavior. We'll discuss it later. So there's a good deal of biological implication of polarization also. So let's just look at the mathematical theory of optical activity. This is due to Jean Augustin Fresnel. It's a very simple and elegant theory based on a remarkably simple insight that linearly polarized light is a superposition of two states of circular polarization. Now, a while ago, I discussed to you with you that you can get elliptical polarization or circular polarization from two linearly polarized states which are orthogonal to each other. So if the phase angle difference between these two linearly polarized states is pi by 2, then you will get circular or elliptical polarization. So circular and elliptical polarization is the outcome of the superposition of two linearly polarized states. But here it is the other way around. That linearly polarized light is a superposition of two circular polarizations. Let us see how. So step by step, we shall first start with the basic idea. So here is Ex, linearly polarized along the x-axis. And we are not making any difference about the amplitude of the two states. So Ex has got the constant amplitude of E naught into x cap. Y has got the constant amplitude of E naught into y cap. The magnitudes are the same, but there's a phase angle difference between the two. So this is for the EX is oscillating along the X axis and EY is oscillating along the Y axis. And the two waves are propagating along the Z axis. So what is their superposition? So that's the question to ask here. So E is equal to EX plus EY. We have done all this work already. So it will be E naught, which is fixed for both, into cos kz minus omega t x cap plus cos kz minus omega t epsilon y cap. Now let us say for right circular polarization means negative angle that is clockwise. Positive angles always go anti-clockwise, I shall remind you. So for right circular polarization, epsilon is equal to minus pi by 2. That's the phase difference. So cos kz minus omega t minus pi by 2. So cos of minus pi by 2, then kz minus kz plus omega t, and that will be equal to, this thing will be cos of pi by 2, then this whole thing, this will be sine kz minus omega t. So let's now see what we have got. For right circular polarization, epsilon is the phase angle difference of minus pi, has the phase angle value of minus pi by 2. So Ex plus Ey will give you right circular polarization for this phase angle difference. So that is what we get. So we call this thing E subscript R, right circularly polarized light, E naught into cos kz minus omega t x cap plus sine kz minus omega t y cap. So that's right circularly polarized light. What is left circularly polarized light like? So there, in that case, epsilon will be equal to plus pi by 2. And so angle will change, it's anti-clockwise, which is left circular polarization. So you have this cosine kz minus omega t plus pi by 2. And then, so in this formula, here, this plus epsilon is plus pi by 2, and so that we are working on here now. And so kz minus omega t plus pi by 2, and then this, and that will give cos of 90 degree minus this angle will give us sine omega t minus kz, and then we want to write it in the argument as kz minus omega t, so we take the minus sign out, and sine is of course an odd function. So the argument, sign change of the argument will change a sign in the function itself. So this is left circular polarization with reference to this phase angle difference. So EL, L as in left. So ER plus EL, let us add these two things and see what we get. ER plus EL, this is EL and this is ER, right? So it is E naught cos kz minus omega t x cap plus sine kz minus omega t y cap. EL is equal to E naught cos kz minus omega t x cap minus sine kz minus omega t y cap. When you add ER and EL, the y component will cancel and you are left with this. What is this? This is just a linear polarized state, linearly polarized light in a, and that is a superposition of two circularly polarized states. So that is the whole idea, that you've got just as circular or elliptical polarization can be achieved, superposition can be achieved by superposing two linearly polarized waves. So say here also we can have linear polarization as the superposition of two circularly polarized states. So I've written something over here in vacuum. We will examine that statement shortly. Okay, so in an optically active substance, this is important. The left and right uh, circularly polarized light rays will propagate along the z-axis with different velocities. This is the case of what is called circular birefringence. Let's try to understand this thing. So there will be a left circular polarized light, there will be a right circular polarized light, and in an optically active substance, they will travel through that substance with two different velocities. And if they travel with two different velocities, note one thing, that velocity of light in a medium is equal to velocity of light in vacuum divided by the refractive index of that medium, which means that for the left circular light and for the right circular light, there will be two different refractive indices. And as soon as you have two different refractive indices, you will have birefringence or double refraction. And if you have double refraction, but in this case, the double refraction is due to the circular state. So that is why this is circular birefringence. Okay. So let's see now. ER is equal to, we just discussed that. And so uh, let's try to understand this thing. Uh, Here, I've written something over here. K that we have over here is defined for vacuum, right? But now that we realize that the two states, left and right states, don't have the same speed, then we shall have to be a little careful. We shall, as we work along, we shall see for ourselves what it is like. So let us say that what is the speed of light in a anywhere the phase velocity of light? It is frequency times the wavelength, right? So when light enters a medium, the frequency does not change. It is the wavelength that changes. So the velocity or phase velocity we write as f into the wavelength or nu into the wavelength lambda. But so if in a medium the wavelength changes, then you can very well ask what is changing on the right hand side of the formula. V is equal to f lambda or V is equal to mu lambda. Well, the frequency does not change. It is the wavelength that changes. So if the wavelength changes, then the wave number k being equal to 2 pi by lambda, that will change. So omega will remain the same for both. So the left state, the right state will have the wave number kr, and the left state will have the wave number kl. And the right state is given by this formula E naught cos krz minus omega tx cap plus sine krz minus omega ty cap. And EL will be equal to E naught cos klz minus omega tx cap minus sine klz minus omega ty cap. And here is the discussion that we had. Omega is equal to 2 pi nu and k is equal to 2 pi by lambda. And for a general wave, the for a wave, the general solution is a superposition of two states, one forward propagation, z minus vt, and the other is the backward propagation, z plus vt. But here, all the waves are moving forward along the z direction, so there is no plus sign in the arguments of all these trigonometric functions or sinusoidal functions, cos or sine. So you just have minus sign. So they are all moving forward. That's our wave function here. Okay. Now let us step by step check what we can do with these terms that we have, these arguments. For the right state, we have krz minus omega t, and for the left state, we have klz minus omega t. So let's now look at this thing. krz minus omega t, step by step, we build it up. Here is, we're taking kr, k subscript r as in right polarized state, circular state, and L as in left circular state. So Kr into Z minus omega by Kr into T, and here it is KL into Z minus omega by KL into T. Okay. Now, if you look at these two formulae, omega by K will give you actually nu into lambda. Omega by K will be 2 pi nu divided by 2 pi by lambda. 2 pi and 2 pi will cancel, and omega by K will be nu into lambda, and that is actually the velocity. So omega by K is the velocity of propagation. So VR for the right polarized light, the velocity is omega by KR, and the corresponding refractive index will be nr, and that will be equal to c by v, or in this case vr. And so vr is written as omega by kr, and so kr will be nr into omega by c, right? And similarly for the left state, the velocity of propagation will be omega by kl. Nl, the refractive index for the left propagation state, nl, will be equal to c by vl. So c into kl by omega. And so kl will be nl into omega by c. And so there it is. Omega is equal to 2 pi nu, omega by c will be equal to 2 pi by lambda naught. So C is equal to omega by k, where k naught and lambda naught refer to the wavelength in vacuum, because now we have to be a little careful, because there is one wavelength for the left state, there is one wavelength for the right state. So what wavelength do we take? We refer to the wavelength in vacuum. So that is what we have. And so that is, so omega by c will give you k naught over here, right? So this is what you have. So then kr will be equal to nr into k naught, kl will be nl into k naught, and k naught is nl. Someone is asking what is vl. Vl is the velocity of the propagation of light in the left circular state, and nl, l and l, nl is n subscript l, vl is v subscript l. It is not v and l next to each other. So an nl is the refractive index, because if velocity changes, then the refractive index will also change. Here is the formula right in front. You can see VL is equal to velocity of light in a medium is velocity of light in vacuum divided by the refractive index. So here is the formula. N subscript L is the refractive index of the corresponding to the left circular state. C by VL. VL is the velocity of light that is in the left circular state. So that is what you have. Okay. KL is not dielectric. KL is K subscript L is the wave number corresponding to the left circular state. 2 pi by the wavelength. The wavelength is changing for the left circular state, because when the velocity changes, the frequency does not change. It is the wavelength changes. So velocity of light in a medium, the wavelength of light in that medium will also change. Okay. Anyway, so now we have to add up the ER and the EL states. And so here is our formula. This is for the ER state, cos KRZ minus omega TX cap and sine KRZ minus, this is, R means wave number for the right circular state. And similarly here, wave number for the left circular state. So linear polarized state is a superposition of left and right circular polarizations. So that is how you see it. So all L and R are subscripts over here. If it is not looking very clear to you, I'm clarifying that verbally. Okay, so now we shall have to add these two things. So here's an X component, here's another X component, here's a Y component, here's another Y component. You add these components, and so what you will get is cos KRZ minus omega t, cos KLZ minus omega t, KRZ is this part, KLZ is this part into X cap. Okay, plus then the y component, E naught sine KRZ minus omega t minus sine KLZ minus omega t. So that's the y component. So now we have this thing. We shall have to work on this thing by using trigonometric identities. So look at this first term up here, cos A plus cos B, cos A plus cos B. The second term over here is sine A minus sine B, where A is KRZ minus omega t and B is KLZ minus omega t. And so cos A plus cos B, trigonometric identity is this, 2 cos K A plus B by 2 into cos of A minus B by 2. Sine A minus sine B will be 2 cos A plus B by 2 into sine A minus B by 2. So there you have that. So let us now look at this thing. A is KRZ minus omega t, B is KLZ minus omega t, A plus B by 2 will be equal to KR plus KZ by 2 into Z minus twice omega t by 2 will be minus omega t. A minus B will cause a cancellation of the omega part. So it is KRZ minus KLZ by 2. The omegas have gone away. Okay. So when you add these things together, you will get in the superposed state. So this thing is now this, and this thing, the sine minus sine, is now this. 2 is a common factor. What we get now is a common, if you look at this equation, you get cos A plus B by 2 as a common factor in both, 2 cos A plus B by 2. So this is a plus b by 2 is this thing. So this is 2 cos a plus b by 2 minus omega t. So I mean, so a plus b by 2 is this. So that is what you get. And then, so this contains time, but the other term does not contain time. A minus b, cos a minus b by 2 and sine a minus b by 2. So those two terms do not contain time. So they just contain the z dependence because the time part has been cancelled here. So this is what you have. Cos kr minus kl by 2 z into x cap plus sine kr minus kl by 2 z into y cap. Okay. Let's now look at this expression closely. If you look at this term at the top, it's not a vector term, it's a scalar term, but it contains time and it contains space. So that is the phase part. Whereas this part does not contain time, but it's a vector. And since it doesn't contain time, we see that it's the amplitude part. Nevertheless, the amplitude is not a constant amplitude. It depends on z. What is the implication of that? Let's now try to understand this thing. So the phase part is the cosine part up here, and this curly brackets, these curly brackets contain the vector amplitude, which is a superposition of the linear, x cap state and the y cap state. But there is a, it's not a constant amplitude. It's there's a dependence on scalar z. Okay, let's see now what we have here. The amplitude is this, as has been written. We write this thing kr minus kl by 2 into z as alpha. Alpha is kr minus kl into z by 2. So we write the amplitude as 2 e naught cos alpha x cap plus sine alpha y cap. So alpha is equal to kr minus kl by 2 into z. Kr is equal to nr into k naught. Nr is the refractive index for the right polarized state. Nl is the refractive index for the left polarized state. Remember, there are two refractive indices over here because there is circular birefringence going on. And k naught, of course, refers to the vacuum wavelength for its definition. So alpha will be equal to kr is nr into k naught, nl into k naught. So nr minus nl into k naught is a common factor by 2 into z, and k naught is 2 pi by lambda naught. So you write this thing and you cancel and you get lambda by lambda pi by lambda naught into z. So z and lambda naught have the dimension of length. So overall, n, the refractive indices are dimensionless quantities. Pi is also, of course, a dimensionless number. So this is a dimensionless quantity. Now, let us try to see what happens because of this, the amplitude. The amplitude is going to rotate in a circular fashion. How so? Because of this thing. If nr is greater than nl, alpha will be positive for positive values of z. So when z is 0, nr minus nl is not 0. Nr and nl have different values, so they will not cancel each other. So when z is 0, alpha will be equal to 0. So you start with a base value of alpha, alpha equal to 0. And then as z is increasing, as the wave is traveling, the superposed state of the right and left circular lights, polarized states, as it is progressing through the optically active material along the z direction with increasing values of z, alpha will increase. And if alpha increases, the polarization, the resultant plane polarized light will start rotating. So this is the amplitude of this horizontal line is the amplitude of the plane polarized light. When alpha is equal to 0, let us look at this equation. When alpha is equal to 0, sine of alpha was 0, cos of alpha was 1. So the amplitude was 2 E naught x cap. When z is equal to 0, just when it is starting to travel through the optically active material at z equal to 0, the plane polarized state is aligned with the x-axis, x cap unit vector. And after that, as z is increasing, alpha is rising. This is with increasing z, alpha is becoming positive. And so this is what you have. If nr is greater than nl, you will have anti-clockwise rotation. And if nr is less than nl, then alpha will be negative for positive values of Z. And instead of going up, you will be going down in the opposite direction. So alpha is negative, so that will be in this arrow is going in an anti-clockwise direction for NR minus NL being positive, NR greater than NL. But if NR is less than NL, this arrow will be turned in the opposite direction. Alpha will be negative and it will go in the clockwise direction. However, Fresnel had a different definition, convention for defining clockwise and anti-clockwise rotation. His definition was that alpha, there's a minus sign difference. It's just a matter of convention or definition, but we should want to look at it also. For Fresnel, there was a minus sign on the right hand side. So if you put a minus sign, then alpha will be defined as a new angle with a minus sign as beta. So for beta, it will be clockwise rotation, and clockwise rotation will be here. It is beta will be equal to minus NR minus NL, will be NL with minus sign, it will become NL minus NR. So that is the convention that you have. Dextro is positive. For Fresnel, going down this way, we are calling it negative over here when you go when you go clockwise, and we call positive when you go anti-clockwise. For Fresnel, the definition was completely opposite. It was that when you go downwise in a clockwise direction, it is positive, and clockwise direction is right-handed direction. So as you face the wave coming towards you, so you say dextro. And levo, when you are going anti-clockwise in the other direction, a left-handed direction, you call it the negative direction. The value of beta will be negative, so it is levo. And if the medium has a thickness d, the final angle with which the wave emerges will be beta, and that is this. So a wave may enter an optically active zone with a certain angle of polarization, and by the time it emerges, it would have turned by this angle beta, NL minus NR into pi d by lambda naught. And in this, we are following Fresnel's convention that for clockwise rotation, which we normally assign a negative sign to, clockwise angular path trajectory is assigned a negative sign, but according to Fresnel, it was positive, and he called it that's the right-handed dextro rotatory phenomenon. And for the other thing, the anti-clockwise, it's the left-handed levorotatory phenomenon. So that is optical activity. Here I shall just discuss a few points about an extension of optical activity. How do you make measurement? Okay, so here it is. So liquid, if you put an optically active substance like sugar in liquid in liquid water, an inactive solvent, water is not optically active. So you make a sugar solution. Sugar is the solute and water is the solvent. You put the two together and then stir and create a clear sugar solution. That liquid will be an optically active material. And so if you make plain polarized light pass through that material, it will produce a rotation of the plane of vibration. And what was found is that for measurement, like I said, um, more sugar, concentration of sugar could be measured from the rotation angle. The rotation angle, the angle by which, so suppose you make light enter a sugar column, a tube full of sugar solution, it will turn by this angle, where d is the length of the sugar solution. So that is what you have. So the rotation angle will be proportional to the amount of sugar in the solution, and that concentration and that amount is measured by the concentration c. I've written something over here. This is not to be confused with the speed of light in vacuum, right? So the concentration is defined as grams of active substance per cubic centimeter of solution. That's how you measure the concentration. The rotation angle is also proportional to the length of the sugar, the tube in which the optically active substance is present. So that's like your D. B beta is proportional to D. Here it is theta is proportional to L. So the length of the liquid through which the light has to traverse or travel through this thing. So theta is jointly proportional to L into C. L is measured in centimeters. C is measured in gram per cubic centimeter. S is a proportional constant, and that is known as the specific rotation of an optically active material. And there is a 10 down there. This 10 makes the centimeter convert to decimeter. So suppose you have got 20 centimeters, you divide that 10 by 10, you'll get 2 decimeters. So the reason for this unit is that certain substances make a very large rotation. So just to make the, I mean, it rotates so fast that you have a few thousand angular degrees. So like I'll just give you some examples. S is equal to 10 theta by LC, right? I mean, that's a constant quantity of any optically active substance, any optically active material. And like in turpentine, theta is minus 37 degrees for a 10 centimeter or 1 decimeter liquid column. Minus 37 degrees means it's a leftward turn, anti-clockwise turn, right? As per Fresnel's definition. Equal thickness of quartz, 10 centimeters or 1 decimeter of quartz, produces huge specific, I mean the angular rotation, 2172 degrees plus and minus. So the plus will be due to the dextro-enantiomorph of quartz, and the minus will be due to the levo or left-handed enantiomorph of quartz. So different substances will require a different definition for the, or scaling for the length of the material depending on how quickly. So in crystals, the definition is reduced for 1 millimeter, not 1 decimeter, 1 millimeter. And so a little discussion on isomers. Same molecular formula for isomers, but there will be difference in the structure, right? So molecular formula may be the same, but different properties will arise due to the 2172 degrees. Yes, 2172. I mean, keep subtracting 360 degrees from that. So the largest number of 360 degree you subtract, then whatever is the angle that is left is the effective angle. So it will be some n times. So how many 360 degree? Divide that by 360 degree and just please check how many 360 degrees. So that will be about 6 or 5 or 6 360 degree turns, or full cycle turns. Anyway, so isomers have this feature that the molecular formula may be the same, but there will be difference in structure. So there's racemic acid. So it appears optically inactive, but it has got equal proportions of right and left-handed isomers. And of course, if it appears optically inactive, it means that the velocity of these two circular states, or the refractive indices of these the two circular states, the right and the left-handed states, must be the same. That's why it is appearing optically inactive, because in that case, if you go by this formula, in this formula, the angle of turning angle will be 0 if these NL is equal to NR. So that's probably the reason why it is looking optically inactive. But it has actually right and left-handed isomers. So you have got optical stereoisomers. Louis Pasteur studied as a part of stereochemistry. And then just to touch on some biological implications, glucose, sugar, is dextrorotatory. Always you will find sugar turning turning light in the right-handed direction, never in the left-handed direction. In fact, left-handed sugar does not occur naturally. You have to artificially fabricate it, and it's harmful for the body. Your body has evolution has designed our bodies to assimilate right-handed sugar, natural sugar. That's why we call it dextrose. It's always right-handed. We don't have left-handed sugar in nature. So we don't have levos, and we can't ingest left-handed sugar. It will start doing all sorts of harmful reactions with all the enzymes and stuff in our body. So that's there. So there's an evolutionary aspect to this thing too. Meanwhile, amino acids, the building blocks of proteins, they are nearly always levorotatory, left-handed. So that is what you have. Antibiotics have some right-handed amino acids, so that's also another thing. So probably that's why if you take in antibiotics, it doesn't actually agree too well with with us when we take antibiotics. So as you can see that nature's evolutionary principle had thought, according to nature's evolutionary Darwinian evolution or evolution in general, natural selection, there must have been certain advantages with right-handed sugar and left-handed amino acids. So that's, but these things could not have been known unless we had studied polarization, this right-handedness and left-handedness. So nature has got its her inbuilt mechanism for making use of polarization. So you can see that polarization is actually deep down. Our bodies are made up of amino acids. Most of the food, much of the food that we eat is made of carbohydrates. So there's a good deal of glucose in that, sugar in that, rice, roti, gehu, chawal, gehu, all these things, right? Wheat, rice, all of these things. So they always will have positive or dextro isomers, not levo. And our building bodies are made of proteins which show levorotatory behavior. Anyway, so it's time up for now. So I think we can stop here. Tomorrow we have one more class, and in that one class we can discuss questions which I can't answer now, and we can also discuss certain implications of quantum information as they come out of polarization, or as they can be related to the phenomenon of polarization. So perhaps I can stop here. If that's Professor Rajendra may please confirm. Yes.
Yeah, yeah. So we can take a few questions.
Few questions. Yes, yes, of course.
So I think this one is answered, right? What is VL, NL, KL is dielectric?
Yes, yes, I have answered that. VL, people might have made some mistake about thinking that V into L or something like that. It is V subscript L, velocity of left circularly polarized light. And similarly, NL is, someone is asking, please provide YouTube link. So I think Professor Rajendra will do that probably in due course. And then
Yeah, the links
NL,
are being shared through Canvas. So
right. Yeah, yeah. So N subscript L, refractive index of the left circular polarized state, like that.
what is Z? What is
Z,
Z?
Z is the depth of the material through which, so let's just see here. Yeah, someone is asking maybe these properties are used in medicine and that is called Q medicine. It could very well be, but certainly polarization is very important biologically. But I'll just first take this question about Z. Let me just see. I'll just show you here. This is this is the diagram. Let's see now. Here, you have X and you have Y. Here, let's just see. Here you have X. Here you have Y. Right? Z is pointing towards you. Light is traveling along the Z direction towards you. You are the viewer. You are the observer. So Z is that. So in a polarized, in an optically active material, suppose you have a tube, right? You make light enter the tube, and the tube contains sugar solution. So at the start of the tube, Z is equal to 0. So let me now go back to that diagram that we have. So at the start, Z will be equal to 0. If you look at this formula, when Z is equal to 0, that is the start. And as light is progressing through that tube, and the tube has got a length Z and it's full of sugar solution, then Z will start increasing in value. And as Z is increasing in value, alpha will also increasing in value. And if this NR minus NL is positive, it will go anti-clockwise. And if it is negative, it will go the turning angle will be clockwise. But In our modern present convention, anti-clockwise angles are positive and clockwise angles are negative. But Fresnel gave the definition that for clockwise it should be positive and for anti-clockwise it should be negative. And clockwise corresponds to dextro, right-handed turn. You are facing it, the light is going clockwise, so it is like stretching out your right arm. Let me just show you with my arm. So you stretch out your right arm and it is going down like this. You're facing the light and it's an anti-glow. I don't know. I think you're looking at my right arm as your left arm. I don't know what it is like. I hope so, because I can see in the camera that my room is looking left to right. I'm actually raising my right hand, not left hand.
Yes, to you it will appear like that, but for us it's perfectly fine.
Oh, okay. Then you've seen the right orientation, correct orientation. So that's the whole idea. There's a very good discussion of all these things in Eugene Heck's book, chapter number 8, section 8.10, optical activity. All sorts of nice diagrams and things are given. So
So
you
does
can
it
look at.
talk about these biological aspects also?
Yes. There's I mean, not to a great extent, but there is optical. So it is 8.10.2, subsection 2 of section 8.10, optically active biological substances. That's the name.
Okay.
You can just look at it
There
because
is there is one more question. What is stereochemistry?
just that thing I mentioned, that structure is different here. Structure is different, but molecular formula is the same. Right? Right-handed sugar, left-handed sugar. Molecular formula will be the same, but the way the molecules are arranged or the structure is designed, the difference will arise. Right-handed sugar is I mean, it's not very good also. You run the risk of getting diabetes if you consume it in too large an amount, but it's not immediately harmful. Left-handed sugar, it could be quite toxic for you. So that's the difference, stereochemistry. But okay, well, I mean, I don't know much about that. Just
All right. So I mean, we don't have the PDF of the book, but the book has a low-cost Indian edition which can be bought from uh, I mean, any bookshop or Indian
Amazon
which
also, yeah,
yes.
because now there's a low-cost Indian edition. But if you want a PDF copy of the book, I can supply it. Will that be all right?
I don't think it would be yeah. So that
It's
could be
not proper
issues,
practice. Yes. Book
right?
title is Optics. Let me just show. Someone is asking you. Sorry, just a minute. Here, here's the book title, Optics. It may now get a new look. Optics by Eugene Hecht and A.R. Ganeshan. So at least relevant chapter of this book, someone is asking relevant chapter, chapter 8. I mean, mine is an old edition, so things can change. You can just check chapter 8 on polarization, a single chapter. So it's a good chapter, and you can also
So the
supplementally
title of the chapter is polarization.
just polarization. You can see, I
Okay.
think,
Okay.
polarization. Yeah. So that is, and there are several. I mean, it's whatever I've spoken about is just a small fraction of this chapter. It goes into extensive mathematical details, especially with reference to electromagnetic aspects of polarization. Here I just said Eugene Hecht, Hecht, optics, Hecht, Hecht. And there's another book, Fundamentals of Optics, by Jenkins and White. This book, Jenkins and White, Fundamentals of Optics. Here also there's polarization, but here it's not a single chapter. There are several other, many chapters here. Like optical activity itself contains one full chapter, interference of polarized light, double refraction. So different phenomena, polarization. So at least I can immediately see 4 chapters in this book. Right, every one of those subtopics has got a dedicated chapter here. Double refraction is a full chapter, and then optical activity is a full chapter here. But I think Hecht's book, in that sense, is more compact. One single chapter contains everything. So that is, yeah. So
Okay. So thank you very much again for the wonderful sessions and interesting sessions related to polarization optics. And we'll be having a concluding session from Professor Arnab Kumar Ray tomorrow. And then we'll start with digital modulation and digital communication techniques from tomorrow onwards. Thank you. We
thank you.
meet tomorrow again at 3 p.m.
Thank you very much.